Carried. So we now move on to the presentation aspect of the meeting, and is Dr. Boyd with us? Thank you for your patience in waiting, Dr. Boyd. I know we had you sign on a little early because we weren't exactly sure when the meeting would end, so thank you for hanging in there. Dr. Lara Boyd is a neuroscientist and physical therapist. She's currently a professor at UBC. She has used advanced brain imaging techniques and developed expertise in mapping how behaviors, environments, and experiences affect brain learning and brain health. Her work includes publishing over 180 scientific papers. She did a TED Talks that had over 30 million views. And in 2020, she became a Wall Scholar, turning her attention to developing understanding of the importance of the arts for brain health. What we know about the brain is changing rapidly as advances in technologies allow us to make important discoveries. And Dr. Boyd's research efforts are leading to the development of new and effective therapeutic methods, some of which have applications for people with Parkinson's, including leveraging neuroplasticity. So please join me in welcoming Dr. Boyd.
Hi, everybody. I think I have myself organized here, and thank you for inviting me today. I appreciate the opportunity to share some of my lab's work with you. I'm sorry we're not in person. That seems to be the trend these days. So it's good to have a great turnout even online, and everyone can be in their slippers. I won't tell you if I'm in mine or not. So today I was asked to speak largely about neuroplasticity. So you'll see that the bulk of my work has actually been in individuals with stroke and also just in healthy brains. And so just a quick kind of background of how I come at this work. So I began my career as a physiotherapist, working with people with stroke and head injury. And I didn't do that work very long because I was imminently frustrated by the fact that I felt that I was trying to solve problems and I didn't understand what was causing them. So I felt like I didn't understand the brain well enough to treat it, quite frankly. And so I returned to school to do my advanced degree and really have spent the last, 20 years now, trying just to understand how the brain works, how it changes when we learn something new, with really an eye towards motor skill learning because of my physio background. So I kind of broke this talk into kind of three hunks, and I'll try to move kind of quickly because I know we're already over time, and it's actually a really nice day out today. I've already been for a run on the seawall, and I highly encourage everyone to get out, and hopefully you'll feel inspired after my talk to get out and do that. So the first part is just explaining plasticity in the brain. How does your brain change when you learn? The second part is kind of talking about why our brain doesn't always do that as well as we'd like it to. And then the last piece is talking about our work in exercise and brain plasticity and learning. And that's where I do have some data from a trial that I helped with at UBC that was in use of exercise in people with Parkinson's disease. So that's kind of a quick overview. I very sadly have no conflicts of interest. I don't have any financial stake in anything I'm going to share with you today. Just kind of a deep desire to understand how things work. Oh, and last, if you have a question, I can't quite see the chat, but I'm happy to be interrupted, honestly, if you want to just jump in. If something's twiggling your brain, I sometimes say things backwards or I get going too quickly. So feel free to jump in, and also I'll be happy to take questions at the end as well. Okay, so let's just start by talking about our neuroplastic brains. And so just to kind of frame this, every time we learn something new, we change our brain. And we change it in many ways, which I'll go over in a second. But this is what underpins all learning, whether it's a new motor skill, a factual skill, the formation of memory induces change in the brain. This happens throughout our lifetimes. In the olden days when I was a master's student, early grad student, we really felt like children were these masterful learners and adults weren't so good at it. Turns out that's not true. Children are masterful learners, but adults are also very good learners, and our brains are also very, very neuroplastic. And that's true whether or not you have brain damage, an acquired brain disease, or you're just aging. And this is all something we're doing right now. So you're constantly changing your brain. And in fact, My favorite thing to say is at the end of this talk, your brain will not be the same as when we started. You'll have changed it just from simply listening and learning. So we know that brain plasticity then is supporting learning. We know that after some kind of neurologic insult or disease, it's contributing to recovery. And so then the question becomes, can we design specific interventions to try to hasten or speed or optimize this brain change that supports the formation of memories and learning? Now, one of the problems, though, that we run into, or an opportunity, maybe we could reframe it as, is that our brain's ability to change, our neuroplastic capacity, is highly dependent on our behavior. So there's no drug that promotes neuroplasticity, and it's not for lack of trying by the drug companies. There have been many drug trials to try to enhance plasticity in the brain, and all of them have failed. So if we don't have a neuroplasticity drug, we know that it's really our behavior that's driving those changes in our brain. We also know that neuroplastic patterns of change, are highly variable from person to person. This is something we're really interested in my lab, is why we can give what seems to be a similar intervention to two very similar people, and we have vastly different responses. And we don't quite understand why, but this is something we're working on really hard to try to start to unpack. And then lastly, it's important for us to acknowledge that neuroplasticity can be positive. So you learn something new, you change in a positive way. It also can be negative. So addiction, for example, is one negative neuroplastic change. So let's say you're addicted to coffee, as I easily acknowledge I am. I get a headache if it gets to be 9 o'clock in the morning and haven't had a cup of coffee. That's because my brain no longer is creating the same types of neurotransmitters and the same types of doses, because I've replaced that with my coffee. That's an example of negative neuroplasticity, and I'll talk more about these as we go on. So the questions are, what are the boundaries of plasticity? What limits and facilitates it? So when we learn something new, when we change our brains, we have kind of three main things that change, and I'll kind of run through these. So we change our brain chemistry, we change our brain structure, and we change our brain function. And so I don't forget to tell you this later, all of these things are happening together all the time. It's not like you have them happening serially. They are kind of interacting with one another, and together they support the formation of new memories. So let's just start by talking about brain chemistry, because this is a really interesting kind of phenomenon, how this works. And so to understand this, you kind of have to understand how the brain works normally. So our brain is made up of billions and billions, probably 80 billion individual brain cells called neurons. And here on the left side of the screen, I have, these are not my images, but these are electron microscope images of neurons in the human motor cortex. So this area that supports movement. And there's some kind of characteristic features of these neurons that are important to understand. So if you just look at this one, you have this big cell body, and then you have this long projection out. This is called an axon. It's just a long connector, if you will, that's going to send an electrical impulse down it. And that may go to another cell body and make a connection. And that's how that's how information is sent from neuron to neuron across the brain. But if you look at these neurons, you notice these branches going off to the side. These are called dendrites. And so this is actually where communication between neurons takes place as well. So each of these individual neurons here, and I'm showing you 1, 2, 3, 4, 5, 6, 7 of them, they're communicating sideways with each other as well through these dendrites. And what happens is these dendrites come right up to another dendrite. They get super close, but they don't actually touch. So there's not a physical connection that allows them to share information. The way they communicate is by sending little packages of chemicals. It's called neurotransmitter, right? Dopamine's a neurotransmitter, and you're all very familiar with that, right? And so these little packets of neurotransmitter are released from one area. Well, it's called a synapse, where these are coming together. It goes across, it connects to another synapse, and that's then a flow of kind of an electrochemical charge that flows across the brain. And that's how the neurons communicate with one another. Now, when we learn, what's really neat is you can change these chemical concentrations very rapidly in the brain, in the order of seconds, milliseconds even, rapidly altering, increasing and decreasing the concentrations of chemicals. And so this is one of the mechanisms that supports the formation of a short-term memory, something that you learn in really short order and recall maybe later on. And so this is the first part of the brain that's able to change to support learning. And we can map that in humans in a couple ways. One of the ways that my group uses is something called magnetic resonance spectroscopy. It's a big crazy word. But basically what it means is in the MRI machine, we can take a region of interest, which I'm showing you here, in this green box, and we can measure the chemical spectrum, the chemical spectra in that box over a period of time. And we can look at different spectra that we're interested in. So these are data from an individual with stroke. So these are MRI images. I should orient you a bit. This one, I'm putting my mouse over. It's as if I slice the front of my head off and you're looking straight in. And what you see here, this is about the midbrain. So this would be the deep basal ganglia area. So you'd probably have your putamen about here and your caudate about there. Over on the other side, this white, this is the stroke in this individual. And we're looking at how the non-lesion cortex is able to release chemicals in response to learning. So just as a quick example, this is an excitatory neurotransmitter called glutamate. And here we're looking at the two sides of the brain, and we're looking at mild versus severe stroke. We can show a difference in the capacity to release this excitatory neurotransmitter. So it's just an example of how we can map this. You can also map it with positron emission tomography, which I'll talk about later in the talk because we have some data from that as well. But so this is our first mechanism for learning. The second thing that changes when we learn is we actually change brain structure. We change it at multiple levels. So I'm going to come back to this same image now that's on the right side of your screen. So one thing that can change as we're learning is we can increase or decrease the numbers of those connections between neurons. So the numbers of dendrites will increase and decrease. We also can change the brain structure in another way. So here, this image on the left, this is actually my brain. And I'm showing you what's called a diffusion tensor image. And what this is showing you, it's like a wiring diagram of my brain. It's a little scary to think about it that way. And so it's showing you all the connections in my brain from place to place. These are those long axons. So we're mapping how water diffuses along these long connectors. And it makes these really beautiful images in humans. And what I'm showing you, what the colors are representing is just the direction. So the red is going side to side, the blue is going up and down, and the green is coming front to back. And another thing that we see with practice and with learning is not just that we're changing dendrites, but you'll see that brain regions that we use a lot will actually become larger in terms of their white matter structure. So for example, if you're a piano player, you will have these very big representations in your brain for your fingers because you're very good at coordinating your fingers. And you'll also see some differences in this midline structure called the corpus callosum, because piano players have this very special talent that they can do two different things with their hands at the same time. It's a crazy hard motor skill. And so we see these structural changes that accompany practice and learning in the brain at multiple levels. So one of the other ways the brain is changing its structure, and this is really exciting to me and in our field, is those long axons, and here's a cartoon of them here, these long connectors. So here's a cell body, a long connector that's called an axon, and here's those dendrites down on the end. Those long connectors, they're actually insulated with fat. So that old insult, you're a fathead, it's actually a severe compliment because you want to have a lot of fat insulating your axons because that allows an electrical impulse to conduct along it without decaying. You can think about this, it's just like the wires in all of our homes. We don't just have bare wires running in the wall. They're wrapped in an insulation, and it enables the conduction very rapidly from place to place. And your brain is very similar. So the brain is wrapped in what's called a myelin sheath. And it turns out that these myelin sheaths are also very neuroplastic. They're thickening and thinning as we learn new things. And they do this to coordinate timing. So you want to have timing arrive at the right place at the right time in the brain. And so that happens by controlling the thickening and the thinning of these myelin sheaths. So you can see that here in the cartoon. And then this is, oopsie, I'm sorry. This is actually what they look like in real life if you look at them under an electron microscope. So what's really interesting about this myelin change is that we can now map it humans, my computer's going ahead without me, we can now map this in humans. And this is actually a technique developed at UBC by our MRI physicists. And what we're able to do is map the amount of water that's trapped by that myelin wrapping around our axons. And we can look at it thickening and thinning. And work from my lab, and this is in healthy people, and we've done this in stroke now as well, shows that as we learn, and we learn a new motor skill in certain brain regions, we'll see the myelin get fatter. So this is a study from that. This is a study where we developed a video game. We had people playing this video game where they have to catch an asteroid and throw it into the sun. So they played it, they did lots of practice. And we found that an area in the brain called the inferior parietal sulcus, and this is on the left, that's why it says LIPS, this area becomes thicker as they learn this task. And this is an area of the brain we know is important for organizing and coordinating visual information with arm motion. And so it makes a lot of sense. If you're going to reach out in space and catch a virtual asteroid in your hand, which this is the task, that this would be an area to become thicker. Now, I'm telling you this story about these data because I want to make one other point of something we discovered when we did this experiment. And that is, let me come back. That is, we looked at the relationship between the speed or the rate of change in individual participants and the amount of change in their brain at the same time. And we found that participants who learned more slowly actually showed more neuroplastic change. And it was indeed patients who actually were struggling during the behavioral learning that showed the most change in their myelin in their brain. And so we kind of infer from that struggle during learning something that's really hard and really challenging actually is really good for your brain. It's causing you to make more myelin, to change your brain structure more through that process. So I want to just take 1 second and circle back to how chemical changes and structural changes when we learn interact. It's really interesting, I think. So I told you that chemical changes can happen really fast. Changes in brain structure, they take time. They probably take sleep. So we see these big changes in structure in the brain happening after a period of sleep. And usually and often that also involves a very specific phase of sleep called rapid eye movement sleep. And that's that phase where your eyes are moving underneath your closed eyelids. It's the time of sleep when we're actually dreaming. If you wake someone up, they will have been having a dream in that phase. And when we sleep, we cycle through these sleep phases through the night. And so we'll have somewhere between 4 to 5 of these sleep cycles happen through the night. That's probably when we're making these structural changes in our brain. So have you all had the experience where you make a short-term memory and then you can't get it later? You think you have it and you don't. So for example, maybe you're a piano player. You're practicing playing the piano, you practice away, and you're like, oh my gosh, this piece is so hard, but I've got it. I've practiced and I've totally got it nailed in this practice session. And you come back the next day and you don't got it. Like, I could do this, I had it, and it's gone. In that instance, you made a short-term memory. You changed the chemistry of your brain, but maybe you didn't practice long enough to actually induce that long-term structural change. So the two have to go together in order to form a permanent memory. I always tell my students, this is why cramming for an exam doesn't work. You might do well in the short term on that exam, but you're not going to remember it later on, right? You won't have actually developed that memory in your brain. And that's because you changed your chemistry when you cram, but you didn't practice long enough to change your brain's structure. I think it's pretty cool. Okay, so the last thing that changed when we learned is we actually changed the function of our brain. So different brain regions are on at different times. They're on with different intensities. And actually, just like with anything else, as we learn something, we can become more efficient with our brain. We can have less brain activity to support that behavior, to support that learning, because we're better at it. So it's not this huge amount. The other thing we see, and that's what I'm showing you here on the left-hand slider, it's a prompt to remind me to tell you, is that also as we learn something very difficult and we get better at it, we're able to use less of our attentional areas of our brain. So in this study, we compared people with stroke to healthy controls. And we showed that in the older healthy controls, but not in our stroke patients, as they learned a new motor sequence, they could turn off the prefrontal part of their brain so they could perform the task without paying tons of attention to it. Whereas our participants with stroke never were able to do that. They're always using lots more brain to accomplish the task. The other really interesting thing about brain function is that our brain is never actually turn itself off. Our brain, even at rest, is highly active. And when we're at rest and we're seemingly doing nothing, our brain will default to a very stereotypic pattern called the default mode network. And it's kind of a rest phase of the brain. And our brain does this kind of automatically through the day. So you don't have to raise your hand, but reflect for a moment. In your AGM meeting that came prior, was there ever a time where you just kind of faded out and maybe you weren't paying a lot of attention and you're like, oh my gosh, I'm not listening, and you come back in? Or you've had this experience, maybe you're driving and you get home and you're like, I don't actually remember driving home, but here I am, lo and behold. Your brain went into default mode network. You took a little brain break. It turns out these are probably very healthy and very good for your brain. We seem to cycle through them during the day. They also change to support learning. So we see changes in the patterns of our resting state activity in our brain that will reflect recent learning. So we think this is another way that the brain's reflecting change, reflecting neuroplasticity, and supporting the formation of memories. Okay, so that's a quick tour of how your brain changes when you learn at a macro level, at a human level. So I just take away from that, all of our brains are really neuroplastic. Doesn't matter if you're old or young, doesn't matter if you have Parkinson's, stroke. Neuroplasticity is happening at multiple levels. Your brain's never resting. And neuroplasticity supports behavioral change and learning. So you learn something, you've changed your brain. So I want to talk about the next part, and these are questions that I ask myself all the time, and that's what I call the promise and the peril of neuroplasticity. So here's my questions. I just told you the brain was awesome, and it is, and we learn all the time, and we change our brain at multiple levels. So why can't we learn anything we want to? Like, I've been trying to become fluent in French my whole life, and I am not young, and I am terrible. So what is my problem? What is wrong with my brain? I don't know, something. My kids have done French immersion and they're fluent and they just laugh at me. So it's okay, I deserve it. Why do kids sometimes not thrive in school? Kids are the ultimate neuroplastic learners. What's happening? Why can't they adapt in that way? And then the one that really devils me is, why can't I help my stroke patients recover better than they do? Why don't we have better effective treatments for Alzheimer's, Parkinson's disease, multiple sclerosis? The brain is this awesome. What's holding us back here? So what's limiting neuroplasticity in these instances? And these are really where my research is centered on. So one of the things is that not all neuroplastic change is positive, and I mentioned this before. And so here's just a few examples of negative neuroplasticity. So a repetitive use injury, a chronic pain. If you have chronic back pain, your brain is very different than someone who doesn't. Drug and alcohol use, addiction in general, and then stress and anxiety. All of these things induce negative neuroplasticity. So here's one that I talk about a lot because I teach in the physiotherapy program at UBC, and everyone's very focused on orthopedic rehab when they come in, our students are. And I have to remind them that in order to help a chronic back pain patient recover, you actually have to remodel the brain. And here's some beautiful data that show that. So this is a study that looked at people with chronic back pain, and they looked at the reactivity of their sensory areas in the brain in these patients with back pain. And what they showed was that the sensory area of the brain in people with chronic back pain is overreactive to every sensory experience. It can be a painful experience. It can be actually something that they don't even perceive. They could be getting touched and it's sub-perception, and you see the brain overreact. And as you rehabilitate that back pain, you also have to change the way the brain is responding to pain in order for it to be successful. And that's why it takes so darn long. And so this is that really neat example of that kind of brain-body connection. So no matter what you're doing in the body, you're always having to change the brain in accompaniment with that. The other one that I've been thinking and talking a lot about recently, because we're all coming into our third year of this just incredible amplified amount of stress and anxiety around pandemics, and can we see family, and are we safe, and do I wear a mask or not? Oh my God, I walked all the way to the grocery store and I don't have a mask. That was me yesterday, etc. Is what is stress doing to our brains? So when we're stressed, we release a hormone called cortisol. And cortisol is actually a great hormone. It's the reason we all woke up this morning was because our cortisol levels went up. So they went up if you woke up kind of on your own and that woke you up, or they went up when your alarm clock rang and it kind of scared you and it spiked your cortisol and you woke up really quickly. So this is a hormone, it's from our adrenal glands, and it's really helpful for all of these bodily functions. It regulates sugar and glucose and blood pressure. It helps with immunity. It helps with arousal. So if you're gonna, run the sun run tomorrow, as you toe the starting line, you're kind of excited. That's your cortisol kind of helping you. You're walking into a test, you feel a little nervous in your tummy. That's kind of cortisol's arousal. And it can help positively affect memory and your immunity and your pain sensitivity. But if we have high levels of cortisol and it doesn't go down ever because we're just constantly aroused or constantly stressed, we find that it can actually impair our cognitive performance. It can also do things like change our immune function, cause us to increase our abdominal fat, change our cholesterol levels, and lead to decreased bone density and losses in muscle. So these are really negative effects of cortisol. And so it seems that, what we really need with cortisol is the right amount. So we call this an inverted U. So if you have too little cortisol, you're just not motivated at all. You can't have no arousal. If you have too much, you're anxious and you have memory impairments. And so then you want to have just kind of this right amount of cortisol. And I have this feeling that all of us are kind of living over here on this curve. We have definitely leaning towards too much cortisol. And so what we find in experiments where you actually manipulate cortisol and you keep it high in animal experiments is one of the things that happens is cortisol actually blocks the brain's ability or limits the brain's ability to be neuroplastic. So it blocks a key chemical in the brain called brain-derived neurotrophic factor, and it limits it. And so if we don't have brain-derived neurotrophic factor, it turns out those dendrites can't be as good as increasing and decreasing their connections. It's a fundamental limiter on the ability to transform a short-term memory into a long-term memory is cortisol. And so it's just something for us to all be super aware of when we're feeling really stressed, that we may be seeing these side effects of it. We're not learning as well. Our brains aren't as healthy. I've been thinking about that a lot in the context of my kids. I have 2 teenage daughters and they're, homeschooled, now back in school, and we're masking, we're not. It's been very disruptive. And I think that all of us, it's going to take us a while to kind of recover from this long-term phases of stress that we've all been in. There's some ways, just as an aside, I hate talking about this and not offering some ideas. There's ways we can manage our cortisol and stress. Meditation is one. If you can do that, I've never been good at it, honestly. I guess my brain's not disciplined enough. But if you practice Buddhist type meditation, you see significant reductions in cortisol and blood pressure. Sleeping 8 hours versus 6 hours a night will reduce your cortisol by 50%. It's big. Exercise, which we're going to talk a lot about next, is a highly effective method for reducing cortisol. And it's my personal way that I keep my cortisol in check as well as I can. And there's some very cool evidence that children who engage in mindfulness programs, there's one we use here in Vancouver in the schools called Mind Up, actually show lower cortisol, higher empathy, more optimism, and significantly lower levels of depression. So there are methods by which we can manage this, but they all require some intention and some work to get there. But it is something to definitely keep in mind. Okay, so the other thing that I want to mention that we know makes neuroplasticity difficult is the fact that it takes huge doses of practice to actually change the brain. So, there's this conventional wisdom, it takes 10,000 hours of practice to master something. I don't know if that's actually true, but it does take a lot, that I can assure you. So the study that I showed you about the Myelin plasticity in our asteroid game, those people practiced that game. They did 10,000 repetitions. So they did 1,000 asteroid catches a day for 10 days. That's a lot of practice. That's exactly why we designed a video game, because we wanted them to do this a lot. We thought we better make it really fun and engaging. But we call this the dose problem in my lab, and it's one of the problems that we confront, especially, for example, in stroke rehab. I think a big reason why a lot of our stroke patients don't recover as well as they should is that we just don't give enough rehab. because our medical system's not equipped for people to do tens of thousands of repetitions of every single task they need to learn. So we need to figure out ways to actually get higher doses of practice, both in the acute medical system, but also, in the evenings when you're alone with your family, and also when you go home and you're an outpatient. So this is a huge issue that we confront. Okay, so a quick wrap up on this part, and that is, not all neuroplastic change is helpful. But if you change your behavior, you are indeed changing your brain. And we know that behavior can remediate negative neuroplastic change, but that the dose required to do this is very high. So, all right, so then this is the part that's the fun. So how could we exploit what we know about neuroplasticity to drive improved human behavior and improved learning? So in my lab, we talk about this as priming the brain to learn. And there's lots of approaches we've used. So we use brain stimulation, we use robotics. Today, I want to talk about a simple one because it's one we can all do, and that's exercise. And so we've done a whole bunch of studies where, we look at the effect of exercise on the brain. So we know that exercise is good for your muscles, it's good for your heart. So we're really interested in what happens in your brain when you exercise. And our studies, we've used what's called a high intensity training approach, or a HIT approach. So we have people come in, and the exercise intervention is only 9 minutes of exercise. So you think, well, you could do anything for 9 minutes. But is, we do three-minute bouts at a very, very high intensity. So in healthy controls, we make them do 90% of their maximal capacity. We have stroke patients that can come in and do 80-85% of their maximal capacity. So you are working really super hard. So you do this 3 hard minutes of exercise, you get a 3-minute break, 3 hard minutes of exercise, a 3-minute break, 3 hard minutes. So that's the intervention. So why exercise? We know that exercise really enhances our capacity for neuroplastic change. It increases blood flow. It increases the formation of vessels in the brain. It makes your white and gray matter thicker, both, and those are 2 different types of brain. So white matter are those long axons that are myelinated. Gray matter is the connecting areas in the brain. You see that brain cells or neurons will grow, and there are more synapses, and you see a greater expression of what we call growth factors, and then a more easy induction of neurotransmitters. And down here is just an example, just a picture, and this is from a mouse brain, a mouse who was a non-exerciser versus an exerciser. And you can just easily kind of visualize the complexity in the neuron of the exercising mouse as compared to the non-exercising mouse. These are our data, and we've shown, and many others have as well, that even a single session of aerobic exercise, this was cycling exercise, increases the amount of that growth factor, brain-derived neurotrophic growth factor, that's circulating in the blood, that we know facilitates learning, that we know helps to make the brain more neuroplastic. So even after 9 minutes of this intense exercise, we see a significant elevation in brain-derived neurotrophic factor in the blood. The other things, though, that we've done that we're more interested in is, does it help learning? So can we translate that into a change in behavior? And so this is an experiment we've done in my lab. We've done it many ways, but I'll walk you through this one particular iteration of it. So we have participants and they're learning a new movement sequence. And this sequence is special in that sometimes it repeats itself and sometimes the targets come up randomly. So the person sitting, I have what's called a Kin-arm robot in my lab. They're holding the arm of the robot, and one of these circles comes up at a time. So you only see one at a time. As soon as it comes up, they move and they hit it with the robot arm, and then another circle comes up and they hit that, and then another one and another one. So they're serially making these movements. And we look at the amount of time it takes to make a response. So we do this, we have people exercise and then practice this task. And so this is what happens. We have a group that is an exercise group. We have a rest control group where they don't exercise. And to keep them from getting sleepy, they watch Planet Earth videos in my lab. They sit on the bike and they watch Planet Earth videos. And what we find is that when we do this and we have exercise and then practice, we have absolutely no effect on learning, 0. There's no difference between resting and exercising, and there's no difference between the repeating sequences that are learned and the random sequences that aren't. So if we stop the experiment here, we would say that exercise has no effect on learning. However, we're really interested in that long-term memory. And remember, I told you that structural change, the formation of a memory, takes time, it takes sleep. So what we do is we bring these people back the next day. They do the task again, but they don't do any exercise. They just do the task. It's a test. It's a retention test, we call it. Did you learn? When they do that, now we see the exercise group shows this huge advantage, this huge amount of learning. What this is called is offline learning. They've actually improved their performance overnight. They exercise, they practice, they go home, they sleep. 24 hours later, they've consolidated their memory, they've shown offline learning. They're better than they were during practice. And this is the effect of exercise. We think it's facilitating that offline learning or memory formation that's happening after practice. So it's really cool. It's really exciting. We've tested this many, many different ways, and it's a very robust finding. So we've also done this in individuals with stroke, and these are preliminary data that are under review. And we find very similar effects after stroke in people with brain damage. And just to kind of give you there's a bit more complexity here than I'm showing. It seems that in patients with stroke, we see a much stronger effect the more complicated the task. So we think we're seeing something where maybe you don't need these exercise facilitations if the task is very simple, but if it becomes a much more complicated motor task, then that becomes a more important primer for learning. So we're kind of trying to understand this. We've just recently finished a huge study. We're just unpacking our data, if you will. So we're catching up a bit. The study was closed for about 18 months. We came back, we finished it, and we're trying to understand it. But there may be something to the idea that the harder the task, the more important the exercise. And we also find something similar in patients who have Parkinson's. So this is work that was done, really led by John Stossel, who I'm sure many of you know. My group was involved because we helped with the mapping of the dopamine response. So this was a study where I'm sure many of you may have even participated in it. People with Parkinson's participated in 40 to 60 minutes of cycling 3 times a week for 36 weeks. And we looked at the ability of exercise basically to preserve the capacity for dopamine release in the brain. So we mapped that using positron emission tomography, so PET scans. And what my group is very good at is we do a lot of brain stimulation. And so there's an approach where you can come in, you can stimulate what's called the supplementary motor of the area of the brain very hard, and it induces a dopamine release in the basal ganglia, in the caudate specifically. And it's kind of like a caudate stress test, if you will. So we were able to show that after this aerobic exercise intervention, the people who participated were much better at this dopamine release. So their caudate responded with more dopamine release after exercise as compared to pre-exercise or a control group. So it just suggests this very important neurobiologic effect of exercise on the brain in people with Parkinson's disease. I just want to kind of wrap this bit up by saying it also probably doesn't matter how you exercise. We use the bike in the lab because we can control it. People tend not to fall off it, so it's a safety issue. But my colleague Teresa Louis-Ambrose has studied exercise tremendous amount at UBC, and she's found that weightlifting has a very similar effect. Weightlifting seems to have a very profound effect, by the way, in women, more so than in men. And it may be because we start off with lower muscle mass. The muscle actually is part of where that brain-derived neurotrophic factor is being released from. So it turns out that activating your muscles and your big muscles through weights may be a really important mechanism. But she's also shown these effects through walking. You can garden, you can dance, cycle, ski, hike, doesn't matter. You see the exercise has these beneficial effects on cognition, learning, and memory. It also reduces rates of dementia. So huge effects, no matter kind of how you get there. A couple other interesting things about exercise I just want to wrap up with is that it doesn't actually matter if you exercise before or after you're trying to learn something. So I showed you we exercise and we practice learning something new. We actually could have had those people practice and then exercise, and you see the same effect. And these are data from a former grad student of ours from UBC, Mark Roy. He's at McGill University, showing that. So it doesn't matter as long as you get that exercise somewhat adjacent to whatever it is you're trying to learn. So there's lots of things, lots of ways that exercise interacts across people. So the effect is not uniform. It's kind of one last important conversation. So we do see differences in age and sex. So, women have a stronger effect from lifting weights than men, it seems. Fitness level may be important. We're running a study right now with a group from St. John's, Newfoundland. It appears that maybe the more fit you are, the more able you are to take advantage of exercise. So that's a study that we're doing comparing people from Vancouver, and oddly, we are oddly fit here in Vancouver compared to the world. We are, may not feel like it, but we are factors healthier than other parts of the planet. And so we're comparing Vancouverites to people from St. John's, Newfoundland, who obviously they have a much worse winter than we do, even after our crazy winter this year, right? We're still not having, 10 feet of snow. So we can still get out and do things. So we're going to actually ask that question. Exercise type is another thing that's important. How long do you exercise? What's the intensity? What kind of exercise? And then it seems like memory systems are differently affected by exercise. And like I said, we have this hint in our data that the more complicated the thing we're trying to learn, the bigger the effect of exercise. So it's something to kind of keep in mind. And then last, there's not a one-size-fits-all approach to any of this. So I mentioned this early on. We see massive amounts of variability in responses to exercise or any other intervention. So roughly speaking, it seems about 60–70% of people show a positive effect to exercise, but not everyone. And I don't know why. It makes me feel crazy. Could be genetics, could be baseline fitness, could be sex, age, some combination of all of the above. We don't understand why. I'm putting this study up here. This is a study we did in individuals with stroke. And these individuals all were the same time post-stroke, had the same stroke location, were using the same arm, had the same stroke size. And we saw a completely different pattern of brain activity out of every single one of them as they learned. So it was crazy. We can't explain it, but there do not seem to be these one-size-fits-all approaches, which is why all of us are so very interested in this idea of personalized medicine. So I would extend that and say we don't want to just have personalized medicine, but we probably also need to have personalized learning. We all probably learn very differently. So your uniqueness of your brain is going to change how you learn, also how you teach, right? Because we're all also teachers. And our big challenge as researchers is to try to sort out these patterns and understand what they mean for the individual who's trying to actually learn and improve. And I think this is our next really huge challenge in neuroscience, is understanding why people are so variable. It requires a lot of time and data, and that's really where we're struggling right now, but we're working on it. We're getting there. So just as a summary of the last thoughts, remember that behavior is the largest stimulant of brain change. And then exercise is a powerful tool by which you can help to shape that change. So it'll affect your memory in the short and the long term. It positively changes your neurophysiology in your brain. I didn't quite show you those data. We have lots of data showing how it changes the brain. Generally makes the brain more excitable. And the net effect is it facilitates an environment that favors plasticity and makes you better able to learn new things. So I think that's really optimistic. I just want to end with that thought that this is a mechanism by which we can enhance both brain health and also brain repair is the idea. And so in my lab, we always say we practice what we preach. So this is actually us. We're at a conference in Chicago pre-COVID, running at dawn along the lake there. It was really pretty. And one of my students dropped back and took that nice picture. And I'm very pleased because I'm out in front of my 20-year-old grad students, but probably not for long. They probably ran me down and thrashed me, and it's all said and done. But anyway, I think it's a very optimistic kind of idea of what we can do with our brains. So I'm very happy to take questions, and I hope I didn't keep you too long or go too fast. It's kind of a fine line there. So yes,
well,
thank you so
thank you
much.
very much. It was a very interesting presentation, and obviously lots of applications for people with Parkinson's. We've often talked about how beneficial exercise is in terms of the motor issues with Parkinson's, but I think also here you've presented another aspect in terms of learning or relearning various activities that can even help with it, obviously will help with the physical aspects too, of dealing with this condition. So we do have some comments coming up in the chat box. It so far looks like mainly it's thank yous, and someone's asking if your presentation will be available on the website. And yes, I do believe we had your permission to record and post.
Yeah.
And
there is one question about a link between chronic pain and stress, and they are linked. So obviously chronic pain induces stress. It actually invokes a cortisol release. And what can happen then is you can get into what we call a negative feedback loop, right? So you're in pain, and so it causes you stress, and you become more stressed, which kind of favors negative neuroplastic change. So actually remember too that stress lowers your sensitivity to pain. So you're more sensitive to pain. So you become more painful. So you become more stressed. Can you see it's going in like a really bad direction? So they can spin off of one another. That's one of the reasons chronic pain is so very difficult to treat in patients. It's really a struggle. Yeah.
And we know that
it induces plasticity in a negative way.
And we know that that can be an issue in Parkinson's disease. Pain can be a really big issue. So
yeah, it's huge.
There is a question from Arnie Johansson. He says, does mechanical manipulation equate to learning? Mechanical manipulation, I'm sorry, Arnie, I'm not sure what you meant by moment. Mechanical manipulation equate to learning?
Yeah, do you mean mechanical movement equate to learning? Is that correct?
Arnie, you're welcome to speak up.
Jump in
if you'd like.
Oh, movement. Yeah, mechanical movement. So yes and no. So it's interesting. Our brains are very specific. So if you're being mechanically moved, let's say a robot's moving you, for example, you learn to move with the robot. So you learn it, but with that aid, right? So in order to move without the robot, you'll have to kind of wean yourself off it. But it can be a way to facilitate the start of movement. Like a bike is pedaling you, and then you reduce the amount it's helping, and you slowly take over. So that can be a very helpful way to start off learning. Yeah.
And I think there have been some research studies done with forced movement, like a bicycle built for two, where the person in front is more powerful, and so the person in behind has to.
Exactly. So it can start it off, right? And so if that's the gateway, then do it, right? Whatever gets you moving is going to be great, and you can slowly wean back the amount of assistance.
And Deborah Harris has a question, wondering what the difference is between default mode in the brain and disassociation, and also how it relates to mindfulness.
So let me start with mindfulness first. So the default mode network, we think that's what people are heading towards when they're being mindful, or they're just allowing themselves to relax and think of nothing. So mindfulness is a little bit tricky because you may be focused on intent. There may be some intention in your mindfulness, or you may be just giving your brain a rest and you're going to default mode. So we do think that may be one of the positive effects of mindfulness, is that enabling you to go to this default mode. It's just a brain break. And so giving yourself that opportunity actually is very healthy for your brain. It's a period of time where spontaneous creativity tends to happen, is when you're in default mode and you're kind of just letting your mind wander from thing to thing. It's also a thing that we don't do. I have a colleague, Todd Handy at UBC. He was really worried because he said we never let our minds wander anymore, because as soon as we have a moment and we're just standing doing nothing, we all do this. We all pick up our phones, right? And like, oh my God, I'm doom scrolling about Ukraine, and my kids are texting. I'm like, where are they? And the grocery store, and my email. Whew. And so anyway, he says we need to be very conscious about putting it down, and we're taking a break. So something I've been trying to do, like I take the bus to and from UBC, and it's a ways. I live in East Vancouver, so I'm like, okay, just sit here. It's hard to do. It's hard for me at least, but it may be important for our brain health. So I'm not sure if default mode is also the same as disassociation, because it's hard to do those experiments where you have people doing that while you're able to scan them. So I don't actually know if I know the answer, but it's more like a research problem than anything else. But we can put people in the MRI and say, just lay there, don't fall asleep, think about nothing, and they immediately go into default mode. It's very stereotypical. So we see that quite often. It's pretty cool. Yeah.
I don't see any other questions in the chat box, but what a fascinating presentation. Lots to think about, I think, with or without Parkinson's, but Parkinson's in particular. I think there's some things here that our community can look at applying that may be quite helpful in terms of we've done the exercise message for a long time now. And there is, as you showed, some wonderful research showing how it can help with symptom management. But I think also learning new things that may be helpful in managing conditions like pain.
Yes.
Obviously, there's a lot of depression and anxiety that come along with this disease. So again, so thank you so much. We really appreciate this. There's a comment that the UBC Brain Wellness Program has an excellent class on practicing mindfulness. We also have done a mindfulness series, and it's been recorded. It's on our website, folks. So there's some starting tools there for you to look at this resource. Thank you again, Dr. Boyd.
You're very welcome. Thank you for the
appreciative.
invitation. And if you do have questions later, feel free to shoot me an email. I'm very easy to find.
All right.
I'd be happy to answer anything. Yeah.
You have a wonderful day. And everyone else too. My goodness, the sunshine here in Vancouver is out. I don't know what it's like in the rest of the province, but I hope you're not getting any more snow. Oh, I do see one hand up. Arlene and Peter, please go ahead.
Just a quick question. We hear sometimes about, you talked about meditation, and we hear about listening to frequencies, tones, sounds, stuff like that. Has any of your research proven that to be effective in any way?
Yeah, we haven't done that research specifically in terms of tones and sounds. We do have an ongoing study, and if you've been to the Brain Wellness Program, you've heard us speak about that there. We're studying effective music on the brain right now, working with the UBC Opera Program and Nancy Hermiston. And that study's underway, but it's pretty neat. We're looking at whether or not those opera students, that the musical training they're undergoing makes them actually better learners. And I think that that's the signal that we see that's facilitating neuroplasticity in their brains. So I didn't mention it, but music's another very powerful tool for brain health. It also is a mechanism, and you're probably aware of this work, that you can use the beat of music to kind of facilitate movement at a certain speed. That's another way that you can use music to kind of pace your movement. So there's just another thought, another kind of thing you can play with in your daily lives.
And we use singing as a way for people to maintain or improve their communication and swallow as well. So it's again another add-on in terms of the benefits of the music.
Yeah, definitely.
Excellent. Thank you.
Mm-hmm.
Anyone else before we close? All right, well, thank you again. And Dr. Boyd has invited follow-up questions. If you think of anything, we can get your questions to her and get your response. And thank you all for spending this beautiful part of this beautiful day with us. Take care. Goodbye now.